we'll be talking about a concept called bias-variance trade-off for models in machine learning. There is something called variance for the data. This is not the data variance, but this is the variance of the model, or basically the model prediction. So first we'll understand the concept of bias variance by simple intuitive examples, and then we'll go into slide of the mathematics and see how we actually get to a good balance of bias and variance. So assume we have a data. This data, obviously we are trying to fit. We have some target variables and we have the x. So this is my feature, and suppose there's only one element of the feature vector, just say x1. So we call just x or, and each of these elements we can call xi, which is a vector. And then we have the targets over here that we need to meet. And what our model is doing is we are trying to predict y, which is a proxy of that. We are measuring the error between them. So assume for a moment that our data looks something like this. Okay. So in real sense, assume that our data was actually a function of a sinusoidal curve. But obviously there will be a lot of noise, so we will not get. So this is our real curve. Okay, so we assume that the data actually came from this. This is our assumption of real. Okay, but we do not know that, so we're trying to just model it hypothetically. This one is your real data, or training data you can call it, on which you have learned it. Okay, and suppose now I have the predictions for these. So for each of these, suppose this is my prediction. Can be near to it, can be close to it. Okay, so these are my predictions. Which are my y's, or y vector. And this one was t. So in essence, my error in predictions minus my actions is coming because of two reasons. The first reason is how different is the data from my assumed curve, or my assumed distribution of the data that I have assumed from the training data that I've got. And the second is given that assumption, how different is my predictions of that assumption. Okay? So instead of, to make things easier, instead of having a direct relationship between my data, which is my t, to my y, okay, assumed there is an indirect relationship. So during training I learn a function. Okay, that function has an assumption, my hypothesis of x, where the distribution where x comes from, and then my y is again drawn from x. So a new x comes, I assume that it's coming from the same distribution, and then I get a corresponding y to it. Okay, y given x. Okay, so this is my relation. So if I try to put this mathematically, my expectation of my loss, okay, is actually a sum of two things. One is how far has my y been away from the initial distribution that I learned about the x during my training. Okay, and we take a square loss and the probability of that x, obviously, because we need to multiply it against or add against all the data elements that we have got, and we are not going with exact data elements, because then we'll have to put a summation. So in integral form we'll just multiply it by px dx. Okay, plus how does the new data that has come fits the initial assumption of the data that we saw or that we fitted during training. Okay? So this part is my difference between my hypothesis of x minus my targets that are coming in the my validation sets in whole square of it. Now this is second property of x and the target, the data set, the combined data set into dx into dt. Okay, so this is my complete loss. If you see this part, the first part of the loss is dependent upon y and your training. So this is what we have learned during our training data. Okay, and this is what we are predicting. So the first part is our actual error in predictions. The second part is this much. The second part, if you see, is not even dependent upon the predictions. Okay, this is just a function of how what we saw in the training, what we are seeing now, which can be a function of, say, noise in the data. Okay. So let's concentrate on this part now, because once we have got learning data and this is the validation errors that we are making, we should know why we are making these errors, and as we can assume this part is constant for the data because we cannot change the noise if it is independent. So if we expand this, we can again assume it as an expectancy of the data. So my expectancy of the data that is coming, which is my y of x given d. So suppose now I am having multiple testing data, validation data, or actual scoring data that are given to me. Okay, so y of x given a particular data minus my what I have learned, hypothesis of x, where it is coming from. Okay, and again we square it. So to square it, okay, this expectancy will remain outside, and expectancy is always in square bracket, so let's keep a square bracket over there. Okay, so this is what we are trying to see in terms of the error, y minus our hypothesis. We can break it down and we can introduce into two forms. The first is the expectancy of the data multiplied by again this y x given d, which is any a particular validation data, hypothesis of x, okay. And close this bracket also, plus again expectancy of the data, which is the same data, validation data that we are getting, y of x given to minus close these brackets. So what is this term saying is, it's the average over the data, what's the expectancy, minus what we have got individually and expected over the data. If we see, this part is from the means of the data, how far we are if we are making multiple predictions. Okay, and this part is that for each of the individual predictions, how far is it away, which is very similar to the concept of the variance. Okay, so this is telling us how disparate my different predictions are if I actually predict on that on multiple copies of the same data, assuming coming from a similar distribution. And this concept tells me that given all the distribution, the expectancy of all the predictions, how far they are from the actual predictions. Okay. So this is my, and this is square, so I can call it like a bias square. So in which case I can say my error, okay, or my loss for the data of the y minus hypothesis of my data is actually a function of bias square plus your variance. And in the earlier slide we had just decomposed our initial term, which is the error term. Okay, so now we can say our total loss was again a function of my validation error, data error, okay, validation data error plus noise. Okay, and this we computed earlier. This is equals to my bias square plus variance, and we have this part again, noise. Okay, so what does it really try to say? Let's try to understand that. So what it is trying to say is that if now I have got a training data and I trained a model on that. Okay, suppose this is my model, call it M1. Now I've got multiple copies of my data to validate it or score it against. And I apply this model on each of these data. Okay, and then I predict it. So suppose this is my space, and I'm assuming that these data have some center, they are like from the same distribution or similar distribution, so their prediction should be somewhere over here. This is my correct prediction. Okay, so let's mark this as correct prediction. So from the first subset, if I score, I get a data point prediction somewhere around here. Okay. Second data I score from this model, I get somewhere over here, then here, then here, then here, then here. Okay. If we try to take an average of all of these things, it will come somewhere around, say, here, the representative point. So let's call this. This is my representative point. I'll put a big circle around it for the representation. Okay, so this is actually my bias, whereas all this spread is my variance. Okay. So this is what we are trying to essentially say. And if we try to slightly overfit the data on the distributions that we have, then that can give me a distribution which are very close in nature. So suppose my all these new data sets, their mean of predictions lies somewhere over here as originally in the above figure. My training data on which I try to fit it was somewhere close but not exactly that. So this was over here. So this was my original training data. Yes, training. Okay. And if I try to now overfit on this data, what will happen is I'll get a lot of dots which are in this region. Okay. Maybe some outside also. And if I take an average of this will be very close to my what I learned in the training data. Suppose this here. In this case, my bias has increased, but if you see, the variance is very less because it is some sort of a, you can say, a condition of overfitting. The reverse will happen if I try to underfit the data. So if I underfit the data, okay, so this is my training one again. Oh, sorry, this is my validation, the means of all the validations. and suppose my training is again at the same point, my training and variations doesn't changes, they are the actual state of the data, so they will be like that, but I can underfit, overfit, and reduce or increase the bias. So in this particular case, I loosely fit that. So what will happen is around this point, because till during training it has not seen this point, so around this point it will be scattered somewhere around this. And if you try to see the mean around it, then you'll find out that means is again very close to the actual data. Okay, but it is, the variance is very high of the predictions. You do not get a consistent prediction all across. So this is your bias and variance trade-off that you can actually arrive with a particular training data, depending upon how do you fit to that data. So essentially, let's try to see it in two different perspectives also. So this perspective is number one. Now, since my error is the minimum possible error that I can achieve, or suppose it is constant within the realm of things. Now this is equals to bias plus variance. Okay, not bias square, not bias. Okay, which means that if I'm trying to draw a curve, suppose I draw a bias curve. So suppose this is my regularization parameter. Okay, so the more I keep regularization, the less it will fit, the less overfitting will happen, and the less is the regularization. If it is 0, then it will be overfitting. Okay, so my bias would be somewhere around here. Let me use some other color for bias. Square of my bias would be somewhere around this. Okay, this is your bias square, not bias. Okay, that is why it's not. Now my variance will come down as I increase the regularization. Okay, but this is linear. So bias was a square, and this will be linear in nature. Okay, so this is my variance. Okay, now do you see this point? It's a good trade-off between my bias and variance. And if we were to plot our errors of the model, the complete total error with our solution, then we will see that even the minima of the error would come somewhere over here to coincide with the balance between the bias and your variance. Okay, so this is your error. Which means that I cannot have a minimum of my bias and a minimum of my variance together in the same model. I can only do a balance. If you are using this model alone, this is the point that you should go for the best trade-off between bias and variance. But this is not always true. As we will understand in the case of ensembles, we will have some other options.